think we are all ready. Great pleasure to have you all here, and in particular to introduce our 40th MARVEL Distinguished Lecture, that is Professor Alexandre Tkatchenko from the University of Luxembourg, where is the chair of theoretical chemical physics. Alex, before moving to Luxembourg, was in Berlin as an independent group leader in the Fritz Haber Institute, and before just as a postdoctoral fellow, following his PhD at the Universidad de Mexico, Autónoma, is it? Yeah. And so he has many distinguished awards. He's a fellow of the American Physical Society. He has the Dirac Medal from the Wotok Association, the Feynman Prize from the Forsyth Institute, and the Gerald Earls Prize. What I found especially notable is that he's very close to a Grand Slam in European Research Council grants, because he has a starting, consolidator, and advanced, but not a synergy yet. That is what would be to complete, and two proof of concept. So incredibly impressive. Today he will be talking about realizing Schrödinger's dream with AI-enabled molecular simulation. Alex, very much welcome.
Thank you very much, Nicola. Thanks to everyone for coming. I'm very happy to be here and give this MARVEL Distinguished Lecture. There's a bit broad topic on how much we have advanced as a community in being able to realize molecular simulations of increasingly large and complex systems by combining first principles of quantum mechanics, statistical mechanics, with maybe second principles of machine learning. This conjunction has really taken us in the last few years by surprise, because we have been able to advance quite a bit. And I will tell you where we stand and what are the outstanding challenges that we all will have to solve as a community. And I see many young people here, which will face a lot of opportunities, I think, in this field and other connected fields. So let me first tell you what I mean by Schrödinger's dream. So what I'm referring to is the famous book of Schrödinger, What is Life?, where he basically argues that we have the knowledge of our fundamental first principles equations in order to even understand, or ask the question at least, what is life from first principles. And I will give you today a bit of my perspective of what we have been able to achieve, in particular by AI-enabled molecular simulations today. Now, if I want to give you a bit more scientific title of my talk, it would be Biomolecular Simulations Beyond AlphaFold and Empirical Force Fields. And I will make it more clear what I mean by these statements as I go through the slides. Now, I want to say that I don't think there's nothing wrong with either AlphaFold or empirical force fields. They're extremely important techniques. In fact, we can actually connect and use those techniques as well. Nevertheless, if you want to understand biomolecular systems, especially complex systems from first principles, you really need to be able to do molecular dynamics at exact first principles accuracy. And that means we have to go beyond these two fundamental pillars of advancement that have been done over many, many decades. Okay, so let me start by going to 100 years ago, so to the founders of our field, Schrödinger, Dirac, and Feynman. And I think you all probably have read parts of these famous works where they've all emphasized that we have now the first principles to really understand very complex systems, but the equations to be solved are too hard, and so we need to find reliable and robust approximations. So I already told you the title of my talk is Schrödinger's dream, really referring to what is life and trying to understand the different components of the cell. Feynman told us that basically, if you want to understand nature, we need to understand the jiggling and wiggling of atoms, and that's what we are all doing. And Dirac told us that we know all the quantum mechanics of many electron systems, at least we can write the equations, but in order to understand the evolution or the behavior of many electron systems requires us to find reliable approximations. And that's what we have been doing. And of course, I don't have to convince you that in the last 100 years, from the paper of Dirac, roughly 100 years have passed, we have advanced a lot. Nevertheless, I think you would also agree with me that despite all of this seminal advancement in the field, we are not there yet to model a living cell at quantum mechanical accuracy, and that's where we would like to go. Okay, so I will give you a bit of a glimpse of what has happened in the last years by combination of what I would call the three fundamental pillars of molecular simulations. So today we really stand on these three pillars. The first pillar is, of course, quantum mechanics. If we are able to solve quantum mechanical equations with increasing accuracy, we get reliable approximations for forces that atoms feel in molecules and materials. But of course, that's just the starting point. That doesn't give us the functionality of real molecules. So if you'd like to understand, for example, the functionality of drugs binding to proteins in our cells, or we want to understand how turbines function, in particular thermal insulators, the function of how solar cells functions, we need to actually understand the behavior of the systems under realistic environmental conditions, temperature, pressure, and general environments such as solvents and so on. And for this, we of course need to use the first principles of statistical mechanics, which usually requires to compute some approximations to the partition function. Now, these were two fundamental pillars, maybe up to 10, 15 years ago, but now we have machine learning, which is the new kid on the block, but nevertheless, to me, has become really another fundamental pillar. We usually consider machine learning as just a way to accelerate our simulations, and many people here in the audience, I think, have worked on proposing surrogate models for either quantum mechanics or statistical mechanics. Nevertheless, I am actually pretty convinced that machine learning stands as another fundamental pillar in this field. And just to give you an example, I just like to mention a recent work of ours where I think illustrates this point. So machine learning is based on statistical learning techniques, and that means that you are able to form representations of evolution of different properties of quantum or statistical systems in large chemical spaces. And if you are able to do that, you can, of course, solve the inverse problem, because you can not only map structures to properties, but you can map properties to structures. And so, for example, in this paper, we have demonstrated how you can design molecules, at least in chemical spaces of small organic molecules. You can actually define which properties you want, and the algorithm, the machine learning algorithm, will spit the exact molecules that obey all of these desired properties. And we also demonstrated that this mapping can actually be done one-to-one. So it's really it's an isomorphism between structures and properties, and you can invert that function quite well. So this just demonstrates one example, but there are many other examples in the literature where machine learning really comes to the rescue and enables us to ask qualitatively different questions than what we have been asking so far with these two fundamental pillars. Let's now come directly to one particular application where machine learning have enabled many, many breakthroughs in the last years, and this concerns the construction of machine learning force fields. So what essentially machine learning force fields aim to achieve is to connect two very different extremes. On the left-hand side, we have electronic structure theory, which is espoused by one Nobel Prize in 1998, given to Walter Kohn and John Pople for the development of dense functional theory and the hierarchy of quantum mechanical methods, respectively. And those methods are very useful, but they are not sufficiently computationally efficient to actually be able to study large systems such as here on the right. On the other hand, we have the Nobel Prize for computational chemistry given in 2013 to Karplus, Warshel, and Levitt for the development of statistical mechanics methods based on empirical force fields. Now, those methods allow you today to study systems with millions of atoms, but nevertheless, as we all know, they are frequently not reliable enough. They're not transferable in different chemical spaces. They don't allow to study chemical reactivity. They don't allow to study many of the processes that are also relevant in proteins, large biomolecular units, and so on. So wouldn't it be nice to provide some methodology that can seamlessly unify these two extremes? And that's what machine learning is trying to achieve. So you essentially produce reliable quantum mechanical data at high level of quantum mechanics, and then you construct a surrogate model that is aiming to approximate the quantum mechanical data as accurately as possible. And if that surrogate model is computationally efficient, this means that you can approach the efficiency of classical force fields eventually, right? So it's kind of an interpolator in this space. Now, we wrote this review article, this review article in this perspective in 2021, where essentially this plot is taken from our review article, where we basically surmised the field of machine learning force fields up to 2021. So the present arrow here shows what systems we were able to study with machine learning force fields that existed up to this moment in the field. So we could study small molecules, we could study nucleotides, dimers of DNA, base pairs, or DNA base pairs basically, or do some reactivity of small molecules. And of course, materials were also possible to study, because materials that people studied, basically their behavior was dominated by chemical bonds, so by local environments. And so machine learning force fields are very, very good to model local environments. But of course, this kind of systems, biomolecules in water, protein folding, biopolymers, were out of scope of machine learning force fields. So what I'm gonna tell you today is that in 2025, just 4 years after our paper, we actually are somewhere here already. So we can actually study proteins in water and larger systems, essentially at quantum mechanical accuracy. There's still many questions in the field. There's still much more assessment that needs to be done. There are many more advances that can be done, but the arrow has moved very, very quickly and very, very far. And this is due to conjunction of many advancements. Advancements in core methodology, in quantum mechanical methodology, advancements in machine learning architectures, advancements in software engineering, advancements in hardware, and so on and so forth. So this all comes together and basically plays in synergy in order to push the ability of our simulations much further. So let me directly show you what we can do today with state-of-the-art machine learning force fields. So this project started in collaboration with the group of Klaus Robert Müller in 2020, actually. The first day of the pandemic, where I had a call with Klaus, and he was starting a sabbatical at Google Brain back then. Now it's called Google DeepMind. And that would mean that he would have access to compute resources of Google research. And so the question was, what can we achieve having access to this computer architecture and the large amount of compute, but also software engineering skills, right? We would have access to people in Google that are great software engineers. And so the question was, well, what can we achieve? Given the situation with the pandemic, my suggestion was to try to push machine learning force fields towards simulating the binding between the receptor binding domain of SARS-CoV-2, the spike protein, with the human cell receptors. Right? Now, I was a bit ambitious, and we, of course, could not achieve modeling the dynamics of this interaction. This is a million atoms or so. But we achieved something which goes towards that goal, and I will tell you what we can do. So what's the idea? Okay, so if you think of proteins and protein-protein interactions, well, all proteins are composed of amino acids. There are 20 natural amino acids. So essentially, the chemical space is something you can enumerate. up to a certain cutoff in terms of interatomic distance. So of course, you could say, let's think of what kind of fragments do we need to produce for which we could do potentially quantum mechanical calculations to compute atomic forces with a rather good accuracy. So then we decided to follow essentially divide and conquer approach. And Oliver, who is really the first author of this paper and who basically led a lot of this work, said, okay, well, why don't we break our proteins into so-called bottom-up fragments and top-down fragments? So bottom-up fragments are just amino acids, pairs of amino acids, and that's innumerable, right? That's not a large number. It's a few million combinations, essentially, that you can create. And this will always be the same for all proteins, right? This will not change, right? That's a complete enumeration of the protein space up to a certain size of your fragments, okay? Then, of course, proteins like this one here, this is a Grampian protein, is composed of different secondary structure motifs. You have helices, you have beta sheets, you have loops, and you have turns. And basically, you could then take several proteins, break them up into fragments, and also design this so-called top-down fragments. Okay. Now, of course, proteins function in water. That means that for the top-down fragments in particular, you need to also include the water molecules around, because water, the entropic effects between water and protein really drive protein dynamics. Okay. So we did that. So we took structures of proteins in water from classical simulations. We broke them up into different fragments. So we have about 4 million fragments. So the large part of the fragments is the small bottom-up ones, and we have a few 100,000 of these top-down fragments from 3 different proteins. Okay. So we take those structures now, and we do as accurate DFT calculations as we can. This is done by a hybrid functional, PB is 0, non-empirical hybrid functional, plus an accurate description of van der Waals interaction using many biodispersion method that we have developed. So we use PB 0 plus MBD in order to compute all of these systems, to compute their energies and forces. Okay, so we have about 70 million forces for all of these fragments. And then we can throw all this data. It takes some time to compute it, by the way, as you can imagine, but Google allowed us to compute this. And so we did this, you know, in vacation time where the computers were rather free. And so we can then take this data and throw it into a flexible neural network architecture. We use the SpookyNet architecture, which is developed by Oliver. It's a transformer architecture using the attention mechanism and also including long-range interactions with explicit physical models, electrostatics and dispersion. Okay, so we take that architecture, we train it on the data. The performance is quite good. And now the question is, once this is trained, in principle, we can apply it to any protein. Right? So let's do this. So let's start from the fruit fly of folding. This is just polyalanine. Okay, this is 15 alanine residues. Okay, we start from a fully extended structure in vacuum. There's no water. Okay, but proteins actually fold in vacuum. This is well known experimentally. Right, you don't need water to fold proteins. So let's start without water, and then we add water. Okay, so we start from a fully extended structure once again, and we fold it. And it folds in about 100 picoseconds. So it goes from an unfolded state, from a linear chain, to a helical structure. This is room temperature simulations, okay? So, okay, we can fold now fruit flies of biomolecules, polyalanine. And the question is, well, what do we learn from here? You can also do this with a classical force field. Do you get any new information? Okay, so let's look now at this plot. So this is the evolution of the structural elements of polyalanine as a function of time in your molecular dynamics trajectory. And I have 2 plots here. I have the classical force field, amber. I could have used any other one. And I have GEMS. So GEMS stands for General Molecular Simulations, which is SpookyNet architecture trained on these 4 million molecules that we have computed with PB0 plus MB. Okay, so the first thing you notice, look here, this is easier to understand. This is a classical force field. It's a harmonic force field, essentially, right, with electrostatics and van der Waals interactions. And so what you see is that you start from this unfolded linear configuration, and you go to an alpha helix, essentially. Once it falls into an alpha helix, it just stays there forever, rigidly, okay? Now compare this to GEMS. So what you see is you start from the fully extended structure. You go then through what we call a wavy structure. It's an accordion-like structure. It would be classified as a turn in terms of biomolecular secondary structure. So it has no direct hydrogen bonds. It has indirect hydrogen bonds, but no direct hydrogen bonds. And then you immediately jump into a helical structure, and you alternate between an alpha helix and a 310 helix. And these two different helical structures differ in the hydrogen bond arrangements. You have hydrogen bonds between residue I and residue I plus 3, or residue I and residue I plus 4, right? So the alpha helix is more compact, 310 helix is a bit less compact. So two things we learn beyond empirical force fields. So the first message of my talk, I said we have to go beyond empirical force fields. Okay, empirical force fields do rigid folds in. They were trained to do so, right? People designed them to get rigid secondary structures because that's what they think should happen. They should be these proteins should form rigid secondary structures. In the quantum mechanical simulation, you get a completely different picture. The folding intermediate is completely different. It's this wavy structure, and then once you get into a helix, you start oscillating between two different helical types. Now, this goes beyond AlphaFold because AlphaFold gives you structures, just usually single structures, right? Of course, you can produce several structures for a sequence, but usually it gives you the crystal structure, and that's what it's supposed to do. Now, here, there is no crystal structure. You dynamically fluctuate between an alpha helix and a 310 helix, right? So this plot shows you that you have to go beyond AlphaFold and you have to go beyond empirical force fields. And I will, of course, have evidence from experiment that this is true. Okay, so we learned two things, and something very important is that the folding trajectory differs. So in a classical force field, what happens is the peptide fluctuates, and you form local hydrogen bonds. And then eventually those local hydrogen bonds go and form a rigid structure. Here, you really start from a collective structure that has no direct hydrogen bonds. The angles are different. They don't qualify as hydrogen bonds. And then you jump into a helical structure and you start oscillating. So the folding procedure is completely different, okay? So it's global folding versus local folding in a classical force field, right? So you learn a lot of new stuff when you are able to do very long time scale molecular dynamics with quantum accurate force fields. Now, by the way, it's well known in experiment that in water, alanine peptides are actually alternating between alpha and 310 helices. Okay, so although we didn't do this in water, but there is evidence from experiment that you have to alternate between the two helices. Okay, another thing we can do with this GEMS approach is we can do, that's pretty slow. I think it's projecting into, okay, that's better now. We can carry out molecular dynamic simulations at any temperature because we have a clean quantum mechanical force field. It's not contaminated by any parameterization at any given temperature, right? And what we learned here is that this polyalanine helix actually stays helical until about 700 Kelvin. At 800 Kelvin, it becomes a mess, right? It becomes a complete blob. And that's essentially kind of confirmed by experiment. So here's an experiment from Gerald's group. And they do exactly the same thing. They have a peptide in an electrospray ionization experiment. So in a helium buffer gas, it flows, right? It has a charged residue, lysine residue here. So it flows through the tube. They measure the cross-section of this peptide, and they basically see that the peptide unfolds at about 725 Kelvin. Okay, so this also agrees qualitatively with our simulations. You cannot do the simulation with an empirical force field. It doesn't make sense, right? Empirical force field is basically feed on 300K data. So you are not allowed to change conditions in this range of temperatures. While with our force field, with the quantum mechanical force field, you can, of course, do that, right? Because you have a clean parameterization of forces at zero temperature, Born-Oppenheimer forces at zero temperature. Okay, so how do we go from here? So I've showed you simulations in the gas phase, but we want to do proteins and water, right? So let's do that for Crumbin protein. So basically, I'm showing you here several things. So again, here we have the scheme. We can prepare this Crumbin protein. It's shown here. We solvate it. It's a box of this 20,000 atoms under the same conditions as what you would do with classical empirical force fields, right? We use the same setup. We pull the protein, we surround it with water, we put it in a periodic box, and we run simulations, okay? First of all, we created blocks, fragments of this protein, the top-down fragments, and we compared our calculation with the reference DFT calculations. As you can see, the GEMS accuracy for forces, for energies and forces is very good. So R square is, essentially 1. While with the empirical force field, you see that the accuracy for energies is not too bad, right? So there is a good correlation between the DFT energies and the force field energies. So that's not too bad. But if you look at the forces on the right, the R square drops to 0.87, and also there's quite some spread in the forces predicted by the force field, by the empirical force field, and by DFT. So clearly our GEMS approach is much more accurate and reproduces the DFT data. So now, okay, so we take this protein and we can run its molecular dynamics, and we can do several things. So for example, we can compute the ensemble of configurations around the native state of the protein. And we can compare to solution NMR experiments. And as you can observe from this plot, just visually, the ensemble computed with GEMS actually resembles the experimental situation way better than the much more rigid ensemble from the empirical force field. So this again agrees with what we saw for polyalanine. Basically, the classical force field just generates two rigid geometries. Let's go a bit deeper into this. So we can compute several things from this molecular dynamics simulations. For example, the Ramachandran map. These are the torsional angles between the different residues. And well, here there's quite some agreement because these are essentially local quantities, right? So you're looking at how the torsion changes between the amino acid residues, and the classical force fields have been trained to reproduce the Ramachandran plot that you have in the PDB data set. Right? So we also reproduce it, but we don't use the PDB data set, right? So we get it from first principles. So this is a good result, right? Your local properties are reproduced by our quantum mechanical force. Now let's look a bit deeper. So let's look at the time correlation function of deviations from the native state. So we start at 0 time, right, where you have the native state of the protein, the native structure. And then as you run the simulation, your Crumbin protein starts deviating from it, right? And you are basically showing the RMSD, the root mean square deviation of between time t and time t plus delta t. What you see is that the amber force field very quickly deviates from the native structure because harmonic bonds fluctuate very quickly, right? So a lot of friction in the system, and you quickly jump out of your native configuration. But then, as a function of time, this plot in the amber force field converges very quickly, right? So it starts oscillating from the native structure very quickly. With the GEMS force field, right? There's quite an opposite situation. So you start deviating very smoothly from the native structure. And then as a function of time, about 200 picoseconds, you actually start deviating much further than the classical force field. So you explore a much larger part of configurational space, okay? Mainly because of long-range interactions. So the interactions in our force field propagate to about 15, 20 angstrom, depending on the hyperparameters. And so basically it's about twice longer than what the classical force field describes, okay? Now, something extremely interesting is looking at this plot. So what is shown here is the basically the projection of fluctuations in the molecular dynamics trajectory to an effective two-dimensional latent space. So these U and V variables are some latent space representation, which in the case of Crumbin actually makes sense because crambin has two salt bridges, which essentially provide like pinning points in the protein, and the protein just fluctuates around them. These are very, very strong interactions, right? And basically they pin the structure of the protein, and the rest of the protein just fluctuates around. So this two-dimensional representation makes sense. And so if you take a classical force field, what happens here is that you start from some equilibrium, some metastable state, you fluctuate around this metastable state, you jump to a different state, you can fluctuate there, and you do this like a random walk, right? This is just a random walk in the configuration, in this latent space. GEMS has, again, completely different behavior. It has a continuous path in configurational space. This only happens because of long-range interactions. If you drop top-down fragments from your learning model and you only train on bottom-up fragments, you get a random walk. Because it's basically given by friction between water and the protein. And there's so much friction that it's just Brownian motion, right, essentially. While in this case, this is clearly not Brownian motion, right? This is really directed motion, and you get a continuous path in a configuration space. You can explain this by a poor physicist statistical model, okay? So you assume that you have double well potentials in your space, and these double well potentials describe essentially separation in terms of the some metric in configurational space and the barrier height between them. And so if you assume that the barrier height is directly correlated to separation, so this means that larger separations mean higher barriers always, then you get a random walk, right? Because there are no long-range dependencies. If you now assume that some states which are widely separated in configuration space are allowed to have low barriers, then you get a smooth trajectory. And there's, of course, a percentage of this, rule-breaking transitions that you can allow, and you can tune this path, really, right? So it really happens because there are configurations which are widely separated in space of the protein, but there's a bunch of low barriers between them, okay? And these low barriers are created because there are long-range interactions, and your system can avoid high barriers, essentially, okay? This only happens when you have a system with long-range interactions, okay? So long-range interactions are crucial. That's what we learn from the simulation. What about experimental observables? So something that people in the empirical force field community never compare to is terahertz spectroscopy. They hate terahertz spectroscopy. Why? Because it measures long-range fluctuations, okay? And this is something you are not able to describe as a classical force field. Usually what people do in protein biosimulation is comparing to NMR spectroscopy. NMR is very local, okay? So you're essentially modeling bonds, angles, and torsions. That's it, right? So you can fit bonds, angles, and torsions pretty easily with empirical force field. So that's why people compare to NMR measurements. But the real measurements that correspond to functionality of proteins in water or other environments are, of course, terahertz measurements, because these are low frequency vibrations, biophonons, if you wish to call them, that span from essentially 0 wave numbers to about 200 wave numbers, right? Much below the water peaks that you get in this system. So we can compute this now, and it turns out that terahertz vibrations have been measured by Woods in this paper, and they've measured 2 spectral regions of the terahertz vibration of crambin in microsolvated crambin, from 20 to 100 and from 170 to 240 wave numbers. So the experiment here is in blue, okay? And our simulations are in yellow, and the amber force field is in green. Now, the absolute intensity, of course, is irrelevant. So you can subtract any constant from these plots. And as you see, an amber force field essentially has nothing, right? It's just flat, right? So it has no peaks. So it cannot describe any of the long-range fluctuations of the geometry of water, of the protein and water around. While GEMS is not quantitatively accurate, it's pretty good here, right? Ignore this region because this is just a Fourier transform, right? We computed using a Fourier transform, so you need to run very, very long if you want really low frequency results. So this is this peak here is just an artifact of the Fourier transform. But as you see in this region of frequencies, we have a very good, I would say, quantitative description. There are some shifts in these higher frequencies, but overall, I would think you would agree that this yellow results obtained with GEMS are qualitatively, semi-quantitatively, accurate, while the amber results are essentially just a constant, right? So there's nothing happening in amber. Okay, so we've done proteins, but we became ambitious, and together with Adil, who is actually in the audience, and I will tell a bit more about his work as a PhD student in the group. We asked the question of, what if you would like to describe all components of a cell? What would it take? Do we need access now to Google and Facebook, or we can actually do this ourselves, right? So we did proteins, protein fragments, and we did it in Google Research Compute. But it turns now that because of Euro HPC investment in Europe, we actually now have academic supercomputers where we can run those calculations, and we don't need Google anymore. And so if you look at the cell, right, the cell is composed of mostly water. As you all know, by the way, modeling water is hard, right? And our water model, by the way, still is not quantitatively accurate. We use PBE0 plus MBD. PBE0 overestimates hydrogen bonds by about 0.5 kcal per mole each. So if you have a tetrahedral water, you still have overstructuring, right? So our water model is not perfect. We are actually working on that. We have good ideas how to improve that. But nevertheless, we are going there, okay? So we have water, 70%. Water should be described as accurately as possible because water is a big player, clearly. And then that 30% is chemistry, which is not water, okay? So 15% is proteins. That's why we start with proteins usually. Then you have 4% of other small molecules. 6% is RNA, 2% is phospholipids, 1% DNA, and then you have polysaccharides. So basically we have this, right? We have water, we have small molecules already in our data sets. So we are missing just these 4 components. And these are minor components, but of course, each of them has to be described with accuracy, okay? So we need basically then, we have proteins, we need carbohydrates, lipids, and nucleic acids. And if you just make estimates of how much you actually need to compute with the same cutoff which we use for proteins, turns out you can do this in just a few months on a big machine. In our case, it's Meluxina in Luxembourg. That's one of the Euro HPC machines. And it turns out you can produce this data in just a few months of compute. That's how things have actually advanced in the last few years. So I think this is quite amazing. Okay, so now data sets is really the key point here. So constructing data sets is a dirty business, which I think Nicola knows very well from all the high throughput computing and so on. Workflows, looking at every component of a data set is an extremely tedious business and an extremely important one, right? So I started working on molecular data sets in about 2018. And the amount of work, if I knew how much work it is required to construct good data sets, I would probably have never started it. But I'm very happy that we did start it. And together with a few people, in this case, with Rob Distasio's group, Alvaro Vasquez Mayagoitia in Argonne Labs in the US, in Chicago. We started constructing this data set. So the first data set we constructed is QM7X data set, which is small molecules up to 7 heavy atoms. And there are 4.2 different conformers and distorted configurations of them. We then followed up together with Janssen, or Johnson & Johnson, to construct data sets for large drug-like molecules up to 80 heavy atoms. We progressed further. As I said, we have data sets for small fragments of biomolecular systems and also protein fragments from this paper that I've just described, from the GEMS paper. And of course, it doesn't end there, right? And data set construction, I think, is the the hidden dirty business of our field, and constructing reliable data sets, choosing what properties you need to compute and so on is really something that I think should be valued much more, because this is something that is widely used by the community. What I also forgot to tell you maybe is that we had an agreement with Google that whatever data we produce, once the publication is accepted, this data becomes public domain. And that's also, I think, crucial, right? That all the data that we are producing using big supercomputers everywhere becomes really available in the public domain, because everyone can use it, everyone can try their models, and we can cross-check, right, that the models that we train on this data actually are giving us robust results, because only then we will have trust by the whole community. And this is continuing. So in Google, again, Oliver and Klaus recently have worked on what they call the QCML dataset, which follows the same idea as the GEMS work, but now basically covering the whole periodic table with fragments up to, I think, again, 8 heavy atoms or 6 heavy atoms. I don't remember exactly. So you basically compute clusters of different atoms in the periodic table using PBE0 plus MBD again, and you saturate these hydrogen atoms. And basically by doing this, you can compute millions of fragments, which in principle cover the periodic table. And you can construct models for chemical bonds between all kinds of atoms, okay? This is extremely important. And again, I think should be really rewarded, whoever is doing such, important and tedious work. Now, DFT, of course, all this data is DFT data, PBE0 plus MBD. Now, as you all know, and I think Nicola knows very well, that's of course not enough, especially for solids. You often need DFT plus U, so you need strong correlation, you need self-interaction corrections and so on. And so we've also looked into this a bit, because ultimately we would like to produce data with the exact solution of a Schrödinger equation. So already in 2018, we asked the question of what happens if we take small molecules and instead of producing machine learned force fields at the DFT level, they actually go to couple cluster level of theory, CCSD parenthesis T. And we actually found in that paper that can change the free energy surfaces and the molecular dynamics also quite a bit. If you compare your dynamics with the DFT functional, with DFT trained data and couple cluster trained data. So eventually we will need to go there. Now, unfortunately, couple cluster calculations do not really scale. So the cost of the calculation is n to the 7, where n is the number of orbitals. And so there's an alternative method in the community, which is quantum Monte Carlo. Quantum Monte Carlo has been used as an alternative gold standard for quantum mechanics for quite some time. And today, together with Claudia Filippi, we have actually demonstrated that you finally can compute forces, accurate forces with quantum Monte Carlo that rival the accuracy of couple cluster. We've done that for small molecules. This work is only for ethanol, right? One of our favorite molecules. And we've demonstrated that QMC can give reliable data as good as couple cluster. The nice thing about QMC is that the scaling is much lower. For forces, depending what approximations you take, you scale n to the 4th to n to the 5th. So that's a much better scaling. And I do foresee that in a couple of years, we could probably do systems on the order of 100 atoms with quantum Monte Carlo. And that means that we could fine tune with quantum Monte Carlo force data on models that were trained originally on the DFT data, right? So we are really going there, and that's pretty exciting that we are finally able to produce force data for such large molecules at essentially exact level of theory. But there's still, of course, an issue, because even if you go to 100 atoms, long range interactions are much further away than 100 atoms. So this is, of course, well known for electrostatics. 1 over R potential is infinite range, right? That's what we all know from our physics education. But also van der Waals interactions and polarization interactions can span quite large ranges. And so I think we will never end to improving analytical potentials, and we should make them as universal and transferable as possible, because we will have to combine machine learned force fields with a finite range with explicit physical model for the long range. I really don't think that machine learning is the appropriate approach to learn long range interactions. Michele Ceriotti, who is not here, might have a different opinion, but the problem with long range interactions is that they are highly dependent on local fragment structures. And so basically it's a combinatorially scaling problem. While for chemical bonds and for local environments, it's a finite problem, right? It's much lower dimensional problem because there are only so many bonds you can actually form, okay? So for that reason, us and many other people are focused on developing universal force fields for different terms, electrostatics, dispersion, and so on. This is just one example of our recent work done by a brilliant student, Almaz Habib-Rahmanov, who actually generalized van der Waals potentials based on the model of coupled Drude oscillators, and basically made a potential that uses only two parameters, and that is twice as accurate as Lennard-Jones potentials. Okay, so finally, let us put all of this together. So we had a GEMS model, as I told you, but the GEMS model was quite a hack. So we had to combine the different terms, the different knobs. The spooky net architecture is actually a quite heavy architecture in terms of the computational cost. And so Adil, when he joined my group, and he's sitting on the back, he asked the question, well, could we ultimately take the best practices from all the different parts of the model and improve it to the extreme and take it to the extreme? So there are few parts on this architecture. So this is a paper which we recently submitted and hopefully will be accepted soon. So the idea is we combine all the data sets, first of all, that we have produced and others have produced. So the QM7X data set of small molecules, the D-SHO data set of molecular dimers, the dipeptide data set taken from SPICE, the aquamarine data set of large conformations of large drug-like molecules, and the GEMS data set of protein fragments. So all of that have been recomputed at PBA0 plus MBD level of accuracy using the FHI Ames code to compute consistent forces, atomic forces in molecules. We then took the most efficient equivariant machine learning force field or machine learning architecture, graph neural network architecture, Socrates, that have been developed by Torben Frank, who is a joint first author on this paper. He is a PhD student in the group of Klaus Robert Müller. This architecture does a very nice trick. So it's essentially as accurate as any competing architecture, such as NeckWIP or MACE. But instead of doing tensor products to enforce equivariance, you actually flatten the tensor in a vector. So you're using all the tensorial information, but only as a vector. And then you do vector products instead of doing tensor products. And there's some tricks with attention. You put different attention coefficients on the different the angular momentum coefficients. And essentially, this gives you almost no loss in accuracy, but a gain of about 50 in speed and memory as well. So that means that with a solar architecture, you can actually fit 200,000 atoms on a single H100 GPU. And you can run about 3 microseconds per atom per MD step, which is about 50 times less expensive than MACE, or I think a few hundred times less expensive than NeckWIP. Okay, so we do all that. So we train this model. We are not only training a local representation, so the local force of an atom in a molecule, but we also train partial charges to molecular dipoles, and we train Hirschfeld ratios to the data that we have in the data sets in order to compute dispersion interactions. So we have a semi-local part, we have a repulsive part, which makes the molecular dynamics stable. We have an explicit description of electrostatic interaction, an explicit description of dispersion interactions. We take all that, we implement this in JAX. Torben and Adil implement this in JAX, which also makes it efficient. We can compute forces, we can run molecular dynamics. So, so we've then done all the blocks of biomolecular systems. They work really well. We can do a protein, we can compute IR spectra, structural spectra, it's very accurate. We can do a glycoprotein, we can do a lipid bilayer. All of this with a single force. Okay. That's completely different to empirical force fields. They are fitted separately to the different blocks, okay? So in principle, you can also do a glycoprotein with an empirical force field, but that requires 10 years of parametrization, okay? In our case, we have a single force field trait on all of this data. And of course, you probably need to produce more data in order to make it quantitatively accurate, but the construction algorithm is clear, right? The training of this architecture takes about a week on a single GPU. So that's also not hard to train or actually fine tune with new data. And once you have this architecture, you can do any molecular simulations at the scale of tens of nanoseconds in about a week on a single GPU, okay? So I think that is a huge progress. I have never dreamed of achieving this in just a matter of 3 or 4 years, essentially from the time we started to work on GEMS. I would have predicted that this would take 10 or 20 years, but you see that all the acceleration in all of these different components, right? Data sets, neural network architectures, the prediction of physical models, and all of this coupled with software engineering tools such as JAX and all the GPUs we have, all this accelerated things by an order of magnitude, right? And so I'm sure that there are still many issues here, right? Because this is too much. So many blocks coupled together. But I can tell you the dynamics we run is completely stable. No issues with the dynamics. We reproduce structural properties and spectroscopic properties of all of these systems. Of course, we have to benchmark more. This is pretty clear. We have to probably go back to simpler systems as well and very, very carefully look at NMR spectroscopy, IR spectroscopy, terahertz spectroscopy, and so on. So there's many things to do. But to me, this solar model, I think I forgot to say the name, we call it solar. So SO3 comes from the Socrates network and LR stands for long range. So we're combining Socrates with long range interactions. And I think the solar model provides a new baseline for molecular simulations, not only biomolecular simulations. You can do other things. You can do liquids, you can do solids, you can do many other things with it, and polymers as well. And so I think it provides a new baseline, and I'm pretty excited about this development. It's all publicly available on GitHub. Just look for solar. That brings me to the end. So I'm pretty excited about this, and I think there are many more things to be done for all the young people in the audience. So with that, thank you very much for your attention.
It was great to hear, and we are open for questions. Please.
Thank you for a great talk. I have a question about the dipoles. You mentioned that the long-range effect can never be learned by machine learning. And when we study a large systems like BioCell, then should we define the dipoles manually, or what about the other things like quadrupoles?
Yeah, that's a good question. So in our case, what we do is we basically we form a partial charge representation that reproduces the molecular dipoles in the data set, right? So for some of parts of these data sets, we actually have computed the molecular dipole, and we make sure that the partial charge representation that we use reproduces those dipoles. So the charges by themselves have no physical meaning, right? They're just atomic charges, but they reproduce the long-range electrostatics. Because the quadrupolar electrostatics and higher order electrostatics can be easily described by the neural network architecture. So we only want to make sure that the long-range electrostatic is actually properly reproduced by this long-range model. That's the only requirement that we have for the long-range. That's why we are only reproducing dipoles. But if you wanted to do spectroscopy, right, and you want to do higher order, then perhaps we will actually need to generalize this and also reproduce the whole electric field of our molecules.
Thanks for the great talk. So I'm wondering how to deal with the sort of the short range interaction between fragments in GEMS model, because so is it partially included also in the bottom up data set, or just one?
Yeah, that's right. So basically in the GEMS model, it also actually uses this ZBL term, which is basically an ionic interaction as you penetrate basically repulsive ionic interaction as two atoms essentially penetrate each other's shells, right, and overlap significantly. So that is actually very important, because if you want a stable molecular dynamics, you need to make sure that the really short range is described correctly, and you don't have any data for this in the data sets, right? Because the data sets, what stabilizes solar, which we didn't have in GEMS, is the QM7X data set. So for all of these different molecules, we have normal mode coordinate transformations, and they lead also to basically data where your chemical bonds are stretched, right? So you have short chemical bonds, you have a bit elongated chemical bonds, and that stabilizes your model. And that's of course learned in this part of the architecture, right? In the semi-local part of the architecture.
Please.
Probably a very stupid question, but at the beginning you said the difference between amber and the reason basically why amber cannot get the folding correct is the long range interaction. But doesn't amber have it, or what's the difference between?
Yeah, amber has electrostatics, of course, treated to infinite range using particle mesh EVAD, and it has Lennard-Jones potential, which is usually cut off at about 10 angstrom. Now, electrostatics in water are of course screened. So basically they are short range in water, they're not long range. And Lennard-Jones potential is cut off at 10 angstrom. So essentially the range is 10 angstrom. The range of our models is 15 to 20 angstrom, right? So that includes much more information. Even if you extend the range a bit, right, you are talking about going from maybe a couple of hundred atoms to 1,000 atoms environments. So that's quite a scaling, right? Because it's volume.
Yeah, it's volume scaling. Yeah. Then I have another question. Do you try also the folding in water? And does it do the same? So nothing changes?
We are trying this at the moment.
Okay.
So we are trying two things. We are trying to look at nuclear quantum effects, first of all. And we are trying to look at the effect of water, with and without nuclear quantum effects as well, right? Because I think these are immediate questions that you would have. So it's a very, very interesting question, what really happens in water. I mean, there are experimental data in water that tell that there is alternation between alpha and 310 helices. And whether we can reproduce the occupation probabilities of the different helices is a great question.
Even the classical potential, even in water, does not see the oscillation?
No, I don't think so. It's much more rigid than experimental.
Yeah. Thank you.
Yeah, Alex, I wanted to ask you a broad comment. In some ways, you probably remember also a few years ago the show, wanting to build even a sort of purpose hardware just to do molecular dynamic simulation with, force fields that are in any case, as inexpensive as it can be, but you can't reach the time scales of a lot of things. And in many ways, here we are in a state-of-the-art atomistic perspective. We still have, 10 to the minus 15 femtoseconds time steps. And so the question is, are we going to be able to do something in which, I don't know, we coarse grain or we abstract or we alpha fold the relevant descriptors and we do dynamics in a different space? What are your thoughts?
Yeah, that's a great question. First of all, you mentioned hardware, right? As specialized hardware. Yeah. I think that's also something we should look at, by the way, because I think with all the FPGAs and all the programmable, hardware that now is appearing, it might be actually interesting as something that we could implement. We usually need more memory than the classical force fields, right? So we are memory bound, so it's important to work on the memory problem. Now, in terms of coarse graining and coupling to AlphaFold, I think, these are fantastic ideas and they need to be done. I mean, what Cecilia Clemente and Frank Noy are doing on coarse graining is extremely interesting, and we're actually collaborating with them by giving them our data from solar and looking whether they can coarse grain. It turns out it's much more complicated because all the coarse graining procedures that have been so far invented are invented specifically to empirical force fields. So they actually use torsions and so on in order to coarse grain. And this doesn't work here because our potentials are anharmonic, right? So we stretch a bond, you get anharmonic contribution. And in fact, that's why the dynamics is way more flexible. because long-range interactions and anharmonicity are at the same energy scale, right? And that's why anharmonicity is driven by long-range interactions and vice versa, right? And so all these coarse gradient procedures need to be generalized in order to apply. Now, coupling to alpha-fold-like architectures is actually straightforward. So alpha-fold can generate ensembles of structures if you break the multiple sequence alignment that they do first. And in principle, we can feed in information about forces, energies, forces, and Hessians directly into those architectures. And we can make synchronization between an ensemble that is being produced and some kind of free energy estimators derived on maybe even the harmonic approximation for each structure in the ensemble, right? So I think that's the way to go. I think doing explicit molecular dynamics, brute force molecular dynamics is great once, right? I mean, that's why G. Shaw had great papers, you know, it folds, it unfolds, and folds, and unfolds. It would be great to do this with these models, but ultimately biology is all about multi-scale, right? And about doing the right thing at every scale, right? Yeah.
Great. I think with this, we thank again Professor Tkatchenko.